Every single second that you watch this video, the processor inside your device executes hundreds of millions of operations. It achieves this speed and consistency not because the physical components are perfect, but through a combination of built-in error-correcting codes and a specific physical abstraction. At the microscopic level, electrical signals are constantly subjected to thermal noise, magnetic interference, and unpredictable voltage fluctuations. To calculate accurately, engineers have to force these chaotic, continuous physical phenomena into strict binary categories. The transistor makes this possible. Physically, it is an electrically controlled switch that reacts to specific ranges of voltage rather than exact values. This graph illustrates an analog signal, a continuous, fluctuating electrical voltage that changes over time. We apply a threshold. Any voltage between 3.0 and 5.0 volts is mapped to a closed switch, a binary 1. Any voltage between 0.0 and 1.0 volts maps to an open switch, a binary 0. By ignoring voltages that fall in the middle, we snap the noisy analog signal into a clean, discrete square wave. Discarding the continuous physical data in favor of two mutually exclusive states provides the predictable environment required for digital calculations to function at scale. Once we have these binary states, we can move from the physical switch to the abstract symbols of logic, starting with the inverter, or NOT gate. This triangle represents a buffer, while the bubble at the output signifies negation. In Boolean algebra, this operation is written as x equals a bar. We map the behavior using a truth table. If input A is 0, output x is 1. If input A is 1, the output is inverted to 0. To handle larger data, engineers arrange these gates into parallel arrays. If we drop an 8-bit string into this block, every bit is processed simultaneously. For a string like 100011101, the output emerges as 01110010. This result is called the ones complement. This demonstrates how grouping individual gates allows hardware to manipulate multi-bit data strings instantly. The AND gate uses a stricter rule. The output is high only if both input variables are high. This operation is written as x equals a dot b. Engineers track this behavior over time using timing diagrams, which compare the fluctuating states of two separate inputs. Notice that output X only goes high during the specific intervals when both input A and input B are at a logic 1. This behavior allows programmers to use the AND gate as a selective mask. By placing a target number over a mask of ones and zeros, we can choose which data to keep. The bits aligned with the ones are retained, while the bits aligned with zeros are reset. This leaves us with the masked result, 10100000. These abstract software commands are executed instantly by routing precisely timed electrical signals through massive physical gate arrays. The OR gate is more inclusive. Its output is high if any input is high. The Boolean expression for this operation uses a plus sign, x equals a plus b. On a timing diagram, the output remains at a logic 1 as long as either input trace is high. This is used in programming to force specific bits to a 1 without changing the rest of the data string. Consider ASCII text. Lowercase letters always have a 1 in bit position 5, while capitals have a 0. To convert a letter to lowercase, we OR it with a mask having a 1 only in that 5th position. This operation leaves the character's unique ID intact, but flips the case bit to 1, effectively changing the letter to lowercase. Basic text processing on any mobile device is the result of binary strings passing through physical OR gates. These basic gates can be physically combined into composite structures, most notably the NAND and the NOR gates. A NAND gate, the inverse of an AND, is written with an overbar covering both variables. We also have the exclusive OR, or XOR gate, which outputs high only when the inputs are at different logic levels. Its counterpart, the XNOR gate, produces a high output only when both inputs share the exact same logic state. This collection of logic gates provides the grammar of digital hardware. By layering these interactions, engineers build complex components, like memory, that drive computation. The shapes we use to design these circuits are standardized visual conventions for human designers. While some diagrams use distinctive shapes and others use rectangular outlines with polarity triangles, the underlying mathematical behavior is exactly the same. These Boolean equations describe physical hardware families, such as TTL and CMOS. The microscopic transistor gates are manufactured and packaged into standardized electronic components, like these 14-pin dual inline and small outline packages. Today, engineers use hardware description languages to script text files that automatically interconnect billions of these basic logic modules. Whether in a simple counting circuit or a multi-core processor, digital hardware is built by translating mathematical Boolean algebra into physical voltages across silicon.